Astronomers believe that every single galaxy hosts a supermassive black hole in its center. And while these supermassive black holes are big, the smallest are only 1,000,000 times the mass of the Sun, while the largest are over 100 billion times the mass of the Sun, they are incredibly small compared to the size and mass of the galaxy itself. So for even the biggest black holes, they represent less than 1% of all the mass in an entire galaxy and are 1,000,000,000 times smaller in volume compared to their home galaxy. And yet, astronomers believe that black holes play an outsized role in the evolution of their galaxies and potentially even control the life cycles of stars throughout the entire galaxy. And, believe it or not, life here on Earth may have been impossible without supermassive black holes. The biggest clue that astronomers have that there is some deep connection between supermassive black holes and their host galaxies is what we call the M-sigma relation. Now, this relation was only discovered around the year 2000, so this represents some of the latest cutting-edge astrophysics research, and it's not all about dark matter and dark energy and inflation. Sometimes it's about relatively simple things like the relationship between black holes and galaxies. Now, in the M-sigma relation, the M stands for the mass of the supermassive black hole. And the sigma is the Greek letter sigma, which astronomers use to represent what they call the velocity dispersion of the gas and stars in the core of a galaxy. You can think of velocity dispersion as the amount of, well, I like to call jiggliness of a clump of matter. If you examine stars moving around, or gas particles moving around, or even bees flying around, you can calculate some average velocity for all those objects moving around. And if that clump has a low velocity dispersion, it means that all the particles or stars or bees have relatively the same velocity. They're all right around that same average velocity. But if the velocity dispersion is high, it means a lot of the bees or particles or stars will have very low velocities and a lot will have very high. There's a wide range of velocities. Why do we use the sigma? Why do we care about this? Well, honestly, because it's easy to measure. If you're measuring properties of a galaxy or the core of a galaxy, astronomers found that it's very, very easy to measure the velocity dispersion, and it's easier to do that than to measure, say, the mass of a galaxy, because you need to do a lot more detailed observations. You need to include a lot of modeling in order to estimate the mass of a galaxy, but the velocity dispersion is directly connected to observations you can make of the width of various spectral lines, and so it just pops right out. And in 2000, astronomers discovered that there's a very tight connection between the mass of a supermassive black hole in the center of a galaxy and the velocity dispersion of the core of the galaxy. The greater the mass of the black hole, the higher the velocity dispersion. Now, normally these kinds of correlations are just that. Correlations are interesting, but they are not causations. They don't prove that something really is deeply connected. It doesn't tell us that the mass of black holes creates a high velocity dispersion or vice versa, and it doesn't prove that there is some sort of common cause. It's just a statistical coincidence, or could be a statistical coincidence. But when it comes to the M-sigma relation, this relationship between black hole mass and velocity dispersion holds over 5 orders of magnitude in black hole mass. That is a huge change for a relationship to hold over 5 orders of magnitude. That's a factor of 100,000. So you take black holes and you find some connection of one mass, and you find a connection to the velocity dispersion, and you look at black holes that are are 100,000 times bigger, and they also match that same relationship, that is telling you something very important. That is telling you that there is likely a very deep connection here. And this is our first clue that black holes don't just sit there in the centers of galaxies and mind their own business. They are connected because the cores of these galaxies, where we're measuring the velocity dispersions, these things are 10 to 20,000 light years across. These are huge. How can a black hole, which is typically no bigger than a solar system, influence the behavior of gas and stars over such an enormous volume? And so that is how astronomers discovered something called feedback. To go on this feedback journey, we need to paint a picture of what's happening in the core of a galaxy. You have incredibly high density stars are crammed together 1,000,000 times more densely than they are in the solar neighborhood. You have gas pockets. It is the downtown. It is where all the action is in a galaxy. Now, all this material, for the most part, ignores the black hole, because the black hole, even though it's large, is just a tiny little point over here compared to the thousands of light years that these stars and gas clouds can live in. But occasionally they do wander too close. And if they get too close, the gravity of that black hole will attract all that material. The first thing that happens is that this material will compress because that black hole is pulling it in and in and in and in. And this compression leads to a lot of friction, which generates a lot of heat. So the temperature of any gas cloud that falls towards the black hole skyrockets to over 1,000,000 degrees, sometimes over 1,000,000,000 degrees. It's incredibly hot temperatures. And when this happens, it releases an enormous amount of radiation, an enormous amount of light. This is an incredibly hot object. It will eventually flatten and start swirling around the black hole, forming what we call an accretion disk. The accretion disk is spinning so rapidly, and it's made of charged particles that are rotating around this black hole. It quickly generates incredibly strong electric and magnetic fields. Normally, magnetic fields aren't that big of a deal. You can ignore a magnetic field. Like the Earth has a pretty strong magnetic field that if you didn't have a compass, you wouldn't even know it existed. But in these accretion disks, the magnetic fields get so strong that they start controlling the flow of gas, the flow of plasma around the black hole. And as material continues to flow towards the black hole, some of it does go into the event horizon, in which case it increases the mass of the black hole and that material is never seen in our universe again. But some of the material whips around the event horizon without ever quite going in, circles around, and then insert complicated physics here that we don't fully understand, launches a jet. And there's a pair of jets racing out of the north and south pole of the black holes. These jets are enormous. They are incredibly collimated. That means they're very narrow. They can extend for up to tens of thousands of light years. That means they can reach outside of the galaxy altogether. And these things are traveling at close to the speed of light. And this is a feeding episode of the black hole. This is what happens when a lot of material crams on to the black hole. But the story doesn't end there. This outflow of energy and momentum and heat has two effects. One, it heats up the gas in the core. It energizes the gas in the core. And this prevents the gas in the core from continuing to fall onto the black hole, because in order to fall onto the black hole, the material in the core has to cool off. It has to be able to cool off so it can shrink down in volume to reach the black hole. If it's too hot, it can simply support itself against that gravitational pull of the black hole and against its own gravitational weight of the gas itself and just hang out being there. When these jets launch, it heats up the gas and it prevents the gas from flowing in, and so it shuts off the black hole. It shuts off this activity, it shuts off the accretion disk, it shuts off the jet. And this sets up a cycle, which we call a feedback cycle, where material falls onto the black hole, a jet launches and heats up the surrounding core of the galaxy. This shuts off the jet. Things take a while to reset. Eventually the gas cools down again, 1,000,000 years later, 100 million years later, falls into the black hole, launches a jet, and the cycle repeats again and again and again. We even have examples, observations, because these jets slam into the surrounding material and they can even inflate bubbles. We see these trains of bubbles from previous jet episodes reaching out of a galaxy. And this is where we believe the M-sigma relation comes from. Every time there's an episode of feeding, the mass of the black hole increases and it increases the velocity dispersion of the core because there's more energy available in the core. It randomizes the gas and stars in the core. It shakes things up. It beats the hornet's nest. It upsets the bees, whatever metaphor you want to use. So what we see here is a connection through this feedback cycle where the more massive a black hole is, the greater the velocity dispersion of the core of the galaxy. And there's a second effect here, and it has to do with stars. In order for stars to form in a galaxy, gas clouds have to cool off. Exactly what happens in the core. You take a gas cloud, and if it wants to form a star, it has to compress down into a very small volume. And in order to do that, it needs to release a lot of heat. It needs to be relatively cold. This happens in the galaxy all the time. It's no big deal. This is part of the regular star formation story of every single galaxy. But when one of these jets comes through, it just blasts the interstellar medium. It blasts these gas clouds. It heats up the galaxy. And when it does that, it can slow down star formation. It reduces the star formation rate in a galaxy because all the gas now has too much energy and too much heat to be able to compress to form stars. And it turns out for most galaxies, this is a good thing. If you just take a galaxy and you take away its black hole, it will use up its available supply of gas in a relatively short amount of time. It will simply burn through its gas. There's only a finite amount of gas in every galaxy. Yes, there is some raining in from outside the galaxy, but that's relatively small. Once it uses up that reservoir of gas, a galaxy simply can't manufacture new stars anymore. So with a galaxy like the Milky Way, in just a few billion years, it can run through all of its material and then simply stop making stars. But the presence of the supermassive black hole and the presence of this feedback mechanism can slow down and moderate the formation rate of stars. It keeps things at a steady pace. It prevents a galaxy from using all of its material at once. So you can have a round of star formation, things are cooling off, gas is falling into the core. Then there's a giant feedback episode and a lot of heat is released into the galaxy. Star formation slows down. No new stars are born for a while. And then the cycle starts again. This keeps it going. This is like the hybrid engine for a galaxy. It's keeping things nice and fuel efficient. Sometimes this can go haywire. Sometimes the black hole can feed too much or be powered for too long, and it can totally shut off star formation in a galaxy altogether. We call this quenching, by releasing too much heat into the galaxy and pushing too much gas away from the galaxy, like physically removing the interstellar medium in a galaxy out of the galaxy altogether. And we've seen this happen, or we have evidence of this happening, where there's no new star formation happening in a galaxy because the supermassive black hole went haywire. And on the other end of the spectrum, sometimes black holes can trigger some extra star formation, especially in the vicinity in the core, where all this jet mechanism is literally compressing the gas in the core, which triggers new rounds of star formation. But for most galaxies, It keeps everything regulated. And what does this have to do with life? Well, if you want to have a solar system with rocky planets with carbon and oxygen and liquid water and silicon and all the elements that make life necessary, you need multiple generations of stars, because every generation of stars creates those elements, then dies, spreads those elements out into the interstellar medium. You get a new generation of stars from that. They enrich the next generation, which enriches the next generation. In order to build a solar system, you need multiple generations of stars to build up enough raw material to build a planet like the Earth. But if all your stars form in a relatively short window, there aren't these multiple successive generations of stars. You just get a few, or 1 or 2 or 3 generations of stars, and then all the material is gone and there are no more new stars. You need to keep a galaxy going for billions of years, 10 billion years, in order to build up the elements necessary for life. And in order to do that, you need a giant black hole. Thank you so much for watching. I hope you enjoyed it. If you did, please like, share, and subscribe. And please go to patreon.com/pmsutter to contribute. I really do appreciate it, and I'll see you next time.